Let's get started on today's notes over transforming linear functions or changing linear functions. And the first thing I want to talk to you about is the parent linear function and a family of functions. What is a family of functions? So a family of functions is a set of functions whose graphs have basic characteristics in common. And then a parent function is the most basic function in a family. So when we talk about a family of functions and we talk about a family of linear functions, they may look different, but their basic characteristics, one of the biggest ones is they will all be a line graphed on the coordinate plane. And now let's talk about transformations. A transformation is a change in size or position of a figure. So first I want to direct you to the graph of the parent linear function. This is the most basic function in this linear family of functions. This basic function is y equals x. Remember, y or f of x is the same thing as y. It's just fancy schmancy for y. So y equals x, you might also see it written as f of x equals x. And it's just the same thing in function notation. And I tell my students, if you ever see f of x and you're confused, you can always just put a y over it. Okay, it just gives us, f of x is just a fancy way of writing y. So in the parent linear function, y equals x, what we're saying here is that every y value is the same as every x value. So on this graph right here, if you look at these points on this coordinate plane, that ordered pair is 0, 0. Let's look at this one up here. It's 3, 3. This one down here is -4, -4. And what do you notice? Every y value is the same as its x value. So that's the most basic linear function. This is the parent linear function. It goes through the origin at 0, 0, and the slope is 1. Rise 1, run 1. That's our rate of change. And now let's look at translations of linear functions. We're looking at translations of linear functions, so I want to refer you to the 4 functions graphed in this coordinate plane. What similarities and differences do you see? I would encourage you to pause the video and write down some similarities and differences. So you probably came up with that all functions have the same slope. That's a similarity. All functions have the same slope. And that slope is up 1 over 1, rise 1, run 1. So the slope is 1. But what do we notice that's different? The y-intercepts. So the y-intercepts are different. The y-intercepts are different. So the graph of h of x, g of x, and k of x are all vertical translations of the graph of f of x. So as you can see, the graph of f of x right here in dark blue, that's our parent linear function. But as you can see, if we move that parent linear function down 2 units, now we've got g of x, which is the graph of f of x, and we moved it down 2, so -2. If you move it down 2 more, you create k of x. K of x is f of x, which is the graph in navy blue, -4. And then if you took that parent function and moved it up 3 units, you would get h of x in green, which is f of x plus 3. So as you can see, that plus 3 right here, this -2 over here, this -4 told me if I just shift or slide that parent function up or down. And what was affected? The y-intercept. So let's move on. Translations of linear functions continued. This example says to graph f of x equals x and g of x equals x minus 3 on the coordinate plane. Then describe the transformation from the graph of f of x to the graph of g of x. Okay, if I graph f of x, that's my parent function. F of x equals x. I know it's going to go through the origin. My slope is going to be 1, and it's going to look like this. Right? It's like that 45-degree angle right there. Positive slope, up 1 over 1. And then I'm going to change colors here, and I'm going to graph g of x. G of x is x minus 3. Well, that means I'm going to have a slope of 1 and a y-intercept of negative 3. So I'm going to go down 3, that's my y-intercept, and my slope is rise 1, run 1. So you can see here, when I graph this line, it looks like that. It's parallel to our parent function of f of x. So what are the transformations and effects on the graph of f of x? Well, we can see that f of x was translated or shifted or it slid 3 units down. But translated is that nice little algebra vocabulary word. 3 units down. And because of that, the y-intercept changed to 0, negative 3. Changed to 0, negative 3. And then there's a really special way that we write this that you need to know, a special way to notate it. Remember, that's just the way we write it. So we can use the substitution property, and that just means we replace, right? We can use the substitution property to rewrite this transformation. So since f of x equals x, anywhere we see x, we can replace it with f of x. Thus, g of x equals x minus 3, right? That's what it showed me. That's what's up there, and I'll change colors here so you can see. G of x up here equals x minus 3, so I just put an x right there. Could be rewritten as g of x equals, well, I'm going to remove that x, and since f of x equals x, I'm going to replace it with f of x. And that's just fancy schmancy for, we took the graph of f of x and we moved it down 3. Now let's look at dilations of linear functions, or stretches and compressions. When we talk about dilations of linear functions, we're referring to the vertical stretches and compressions of the function. So refer to the 4 functions on the right. What similarities and differences do you see? So I would encourage you to pause the video and write down some similarities and differences. Okay, so let's look at those similarities and differences. All the functions have the same, what do you notice? Y-intercept. All the functions have the same y-intercept, which is the origin. So they're still going through the origin. What else? All the functions have a positive slope. Do you see that? They all go from lower left to upper right. That's a positive slope right there, right? Negative would look like this. So they all have a positive slope. Oh, I'm not writing that right. All functions have a positive slope. Functions have a positive slope. But what do you notice about the steepness? You've got some that are steeper than others. So we just noticed that really the slope has changed. We've got some that have a really flat slope and some that are steeper. So the slope is what has changed. When the number in front of f of x is greater than 1, we call this a vertical stretch, and the line becomes steeper. When the number is less than 1, we call this a vertical compression, and the line becomes less steep. So looking at this graph a little more closely, we can see that our parent function is f of x equals x. And then we have these 2 lines that are steeper than f of x equals x. We have this purple line here that is a 2 in front of f of x, and then we have this green line here that is 4 in front of f of x. Those are vertical stretches. When that number is greater than 1, it's going to stretch that graph vertically and make it steeper. Obviously, those numbers, the bigger they get, they have a steeper slope. Because if my slope is 4, I'm going to be rising 4 and running 1 versus 2 where I'll be rising 2 and running 1. Very different. So it's going to make a slope that's steeper when it's a bigger number in front of the f of x. And then let's look at the graph that's in red, and I'll change the color up here to red. The graph that's in red, that's not as steep. And what do you notice that's in front of f of x? A 1/4. So when you have a number in front of that f of x, or really in front of x if you're writing it the other way, that's in between 0 and 1, it's going to create a slope that's flatter. It's going to be less steep. Because if my slope is 1 over 4, I'm only going up 1 over 4. It's going to make that line much less steep. Okay. Now let's talk about translations and dilations on the same coordinate plane. Here's an example of multiple transformations on the same coordinate plane, specifically a translation and a dilation. So this example says to graph f of x equals x, which is our parent linear function, and g of x equals 2x minus 3 on the coordinate plane below. Then we'll look at what's kind of going on here. So we've got f of x equals x, which is our parent linear function, goes to the origin, slope is 1, up 1 over 1. And it's going to look just like this. So that's f of x. And then g of x, I'm actually going to graph it in a different color. G of x is 2x minus 3. So we know how to graph linear functions at this point. My slope is the number in front of the x, so the slope is 2. And then my y-intercept is negative 3. So I'm going to graph that y-intercept first. And what do you know? Wait a second. When we looked at the transformations earlier, we saw that this right here, what does it do to that y-intercept? It moves it down 3 units. Okay, or we've got our basic linear function, which goes through the origin, and we're moving it down 1, 2, 3 units. And then the slope is 2. So instead of rising 1 and running 1, we're going to be rising 2 and running 1. Rising 2 and running 1. Okay, so there's the slope of my line. So what are the transformations and effects on the graph of f of x? Well, we can see, and this one's g of x, we can see that f of x, what happened to it? Well, the graph has been translated 3 units down. Been translated. Translated, what's that mean? Just shifted or just slid, like the whole thing just moved down. Translated 3 units down. That's important, down. What else happened? The graph has been vertically stretched by a factor of what? Vertically stretched by a factor of 2. That's how you say that. It's been vertically stretched by a factor of 2. This factor right there. It's been vertically stretched by a factor of 2, which creating a steeper slope. Because it's been stretched by a factor of 2, this slope is steeper. If I compressed it by a factor of 1/2, for example, it would be flatter. It wouldn't be as steep. So now let's look at this special way to notate this transformation. Again, we can use this substitution property, which just means we're going to replace something with something else. We can use the substitution property to rewrite this transformation. Since f of x equals x, anywhere we see an x, we can replace it with f of x. Thus, g of x equals 2x minus 3. And I got that from this equation up here at the top that says g of x equals 2x minus 3. Well, if f of x equals x, then instead of writing 2x minus 3, I can write that g of x equals 2 times f of x minus 3. And I still know that my slope is going to be 2 and my y-intercept is negative 3. And I know that that slope is 2 because f of x is our parent function. It would be something different in, say, example algebra 2 if f of x wasn't equal to x. So let's move on to reflections of linear functions, and it's the last transformation that we're going to talk about. Now let's talk about reflections of linear functions. So refer to the functions graph to the right. I only have 2 on this one. What similarities and differences do you see? Well, the slopes look to be the same, correct? However, look to be the same, but one is positive and one is negative. One is positive and one is negative. So as you can see, they have the same y-intercept here. My slope is up 1 over 1. Here's my parent linear function, f of x. And then g of x, over here, it says negative f of x, okay, which means if, let's see, if f of x equals x, and f of x is fancy for y, g of x equals negative f of x, that's saying negative y. Or instead of negative, I like to say opposite y. So all of my x values will have an opposite y value, which creates this look right here. The graph of g of x is a reflection, which is a mirror image, across the x-axis. You may recall in transformations in 7th grade or 8th grade that if you reflect something across the x-axis, it becomes opposite y, and you probably use mapping notation that look like this, opposite y. So x, y, boom, became x opposite y. That was how you mapped out reflections on the coordinate plane, opposite y. So that reflects it across the x-axis. So this moved over here, and this moved up there, and reflected it across the x-axis. So remember, and let's write that here, all y values became opposites. And remember, f of x just means y, or the output value. So when a negative is placed in front of f of x, we will take the opposite of all y values, thus reflecting the line across the x-axis. And now we're going to move on to our last and final task, looking at multiple transformations of linear functions. In looking at multiple transformations of linear functions, we're to graph f of x equals x on this coordinate plane, which is just our parent function, and g of x equals negative 4x minus 1 on the coordinate plane. Then describe the transformations from the graph of f of x to the graph of g of x. So first, let's graph f of x. That's just our parent linear function right here. It looks like this. And now we're going to graph g of x, and I'm going to do it in a different color. So for just the sake of graphing this, since it's in slope-intercept form, y equals mx plus b, we're just going to identify our slope and our y-intercept. So our slope is negative 4, and our y-intercept is negative 1. So what do we graph first? Our y-intercept, our beginning point, negative 1. So what do you notice automatically? This linear function has been translated or shifted down 1 unit. That's what affects my y-intercept, is that translation. And then my slope is not positive 4. I'm not rising 4 and running 1 this way. Okay, I'll be rising 4 and running 1 the other way. Or a lot of students like to graph, okay, if it's negative, I'm going to go down 4, and then I'm going to go this way. But could I also go up 4 and go this way? Wouldn't those points fall on the same line? Yes, they would. And I've got a negative slope here. So this right here is the graph of g of x. So what transformations and effects on the graph of f of x took place here? Well, the graph has been translated 1 unit down, and I'm just going to write it kind of shorthand. Translated 1 unit down. What else? It's been vertically stretched by a factor of 4. Vertically stretched by a factor of 4. And I know you want to talk about that negative because we wrote our slope as negative 4, but the 4 is what stretched it. The negative is what flipped it or reflected it across the x-axis. So it's also been reflected across the x-axis. Okay, so a special way to notate it. We can use the substitution property to rewrite this transformation. Since f of x equals x, anywhere we see an x, we can replace it with an f of x. You're used to this by now. Thus, g of x equals negative 4 times x minus 1. But since f of x equals x in this case, it could be written as g of x equals negative 4 times f of x minus 1. And that concludes your notes over transformations of linear functions. I hope it was helpful.